PowerPoint popped up. All right, there we go. So just as a quick reminder of what we were talking about, we're still doing a little bit of review. Then we're going to get on to some newer concepts and mix in some review with that. But we've been talking about energy, equilibrium constants, and we ended with this question on enzymes. The next thing we're going to talk about is hydrogen bonding and water in general. Now, biochemistry is chemistry of life, and life as we know it is surrounded by water. The cell is full of water. So we have to really understand how hydrogen bond works and how the water molecule itself works on a biophysical level. So hopefully you remember from Gen Chem, water here has a partial negative charge on the oxygen, partial positive charges on the hydrogen. It's a tetrahedral when you look at the non-bonding pairs, but it's in a bent geometry. What water can do that's really special is that it can form what are called hydrogen bonds, right? And these are non-covalent bonds. So remember, they are non-covalent, they're not covalent bonds. And what a hydrogen bond is that if you're just looking at water, the partial positive of a proton of water will form this non-covalent interaction with the partial negative of one of the lone pairs of water. Now, water's not the only thing that hydrogen bonds. A lot of molecules inside the cell hydrogen bond, so DNA can hydrogen bond, protein can hydrogen bond. Basically, when looking at hydrogen bonds, the only atoms that can hydrogen bond are going to be oxygen, nitrogen, and fluorine, or a hydrogen connected to oxygen or nitrogen. This is a big thing that I see every semester, yet some of you are going to get it wrong. So I'm going to make this giant box. Carbon or hydrogens attached to carbon can never hydrogen bond. So like if I have this carbon, hydrogen, that can never be in a hydrogen bond. Carbon and hydrogen are not polar enough. You need to have your hydrogen be a partial positive charge. Hydrogen bonds themselves are incredibly important when it comes to biochemistry. It's the reason why proteins fold. A lot of interactions are dictated by hydrogen bonds. So I like to joke that if you don't know an answer in biochemistry, you don't know why something happens, just say hydrogen bonds. Like 10% of the time you'll be right. Hydrogen bonds are that ubiquitous and they're that important to really understand the chemistry of life. So just as a little warm up and to see if we understand that concept, we'll take a minute here and see if from this image, if you can tell me what's going to be a hydrogen bonding acceptors and donators. And then if you can move on from that, draw water with 4 hydrogen bonds if you can, just to make sure we're comfortable with the idea of hydrogen bonds. So I'll let people have a minute or two to do that. So when thinking of hydrogen bonds, remember NOF, nitrogen, oxygen, fluorine. So if I was going to look at A, what can hydrogen bond? This could be in part of a hydrogen bond. This could be a part of a hydrogen bond. This could potentially, although it would be a weak hydrogen bond. This could be in a hydrogen bond. That could be in a hydrogen bond. That could be in a hydrogen bond. No carbons. Never ever tell me a carbon's going to be in a hydrogen bond. I will cry if you tell me a carbon can be in a hydrogen bond. B. There's a hydrogen bond. There's one. There's one. There's one. C. These oxygens can be in a hydrogen bond because they're negatively charged. NH3 plus, sure can. OH, sure can. Not this hydrogen. That's connected directly to a carbon. So it is not polar enough to be in a hydrogen bond. And B, I will draw that since we're a little bit behind. So here's water. So it can have 4 hydrogen bonds. It can have 1 to each lone pair. And each hydrogen can be in a hydrogen bond with a separate water molecule. So this center water has the maximum number of hydrogen bonds it can have. This is what happens in ice. When ice forms, basically all the water molecules arrange themselves in such a way that they all have 4 hydrogen bonds. In water, liquid water, each water molecule has like 3.1 hydrogen bonds, something like that, where most of them have 3, some of them have 4. And when you're looking at liquid water, the molecules move so fast that they're constantly breaking and reforming these hydrogen bonds. But the idea of hydrogen bonds is an idea we'll come back to a lot in this class. It explains a lot about why life is the way it is. But yeah, that's the basics on hydrogen bonds. Any questions about those ideas? All right, if not, we can move on then. So when a nonpolar substance interacts with water, nonpolar substances cannot hydrogen bond with water, like that carbon example I was talking about. And water really wants to hydrogen bond with any other molecule. Water, being a polar molecule, will try its best to neutralize its own polar charges. So when it comes into contact with nonpolar molecules, what happens is called the hydrophobic effect. And the hydrophobic effect is water will form this cage, this like Clathrin cage, and it will force all the nonpolar molecules together. So it's going to form this cage and keep pushing them together. What this does is that it minimizes the amount of water molecules that have to interact with a nonpolar substance, because all these water molecules around the nonpolar substance aren't that happy. They can't hydrogen bond with the nonpolar solute, so they're not happy. But the reason this happens, and is shown here in the picture below, if you have individual oil droplets, the amount of water that has to interact with these oil droplets, it's much bigger than in picture B, where you push them all together. Now less water molecules have to interact with this oil droplet. So a common misconception of the hydrophobic effect is that hydrophobic molecules are the driver, or they're the ones who care about the hydrophobic effect. They're the ones who want to aggregate. And that's not true. Hydrophobic molecules don't care who they interact with. They're hydrophobic. They're fine interacting with anything around them. Water is the molecule that is driving the hydrophobic effect. It is water who is pushing all these hydrophobic molecules together because they cannot hydrogen bond with them. When we form this cage, we are creating some order, right? Entropically speaking, it is more disordered if the oil droplets are spread apart in the water. So in picture A, it's good entropically. Chaos is increasing, but it's bad enthopically. Enthalpy, we usually talk about that as heat. Enthalpy is also bonds, right? The more bonds you have, the lower your enthalpy. So, or the more negative it is. So this is bad for enthalpy because we aren't forming these hydrogen bonds. While in B, our entropy decreases, but our enthalpy becomes negative. I got my arrows mixed up there in A. Not as negative as A. Not as negative as in A, becomes more negative in B. Because you're forming more hydrogen bonds, you take a hit in entropy, but you are forming more bonds, so that is good. Questions about that idea? All right, then we'll move on. So just since we're going to be working with water a ton, it's very important that we can look at molecules and determine what's hydrophilic, which likes water, and what's hydrophobic, which doesn't like water. So I have a poll here, and I want you to rank these these 5 molecules in order of most soluble to least soluble. So see if you can do that. Put the poll up so I can see what we land on. But take a minute or so to see if you can determine which molecule is most soluble, which one is least soluble. All right, so a couple more seconds and I'll give the answers. And those of you watching on YouTube, make sure you are trying this, not just skipping to my answers, because doing is how you learn. All right, most soluble. Looks like we have a split between C and E. The answer there is C. That is the most soluble. Why? Because every single group and C can hydrogen bond. You got nitrogens and hydrogens on each side. They can form hydrogen bonds. That carbonyl carbon can form hydrogen bonds as well. Well, the oxygen can. So everything can hydrogen bond. That is perfectly fine being with water. The next one is B, because all you do is you take one of those nitrogens away and put a carbon. So you lose a hydrogen bonding group, but it's still pretty good. E is our third one, where you still have a carbonyl group, so that can hydrogen bond, but you have now lost all the nitrogens. You just have carbons. Fourth is A. Now you have an ether. Ethers aren't great at hydrogen bonding, but they still can hydrogen bond marginally, so you're going to be somewhat soluble. D is the last. No hydrogen bonding groups here, just a bunch of carbons. So this is hydrophobic. It's not going to be soluble in water at all. So CB, EAD, seaweed. Any questions about that idea? All right. The last thing we're going to talk about in this slideshow before I move on to the next one is the movement of water and solutes in and out of the cell, which is osmosis and osmotic pressure. When we talk about cells, cells are full of dissolved things in water. So proteins are dissolved in there. A bunch of salt is dissolved in there. So it's a very concentrated environment. And when you dissolve something in water, you create what are called colligative properties, or they have what are called colligative properties rather. And talked about this in Gen Chem 2, so it's been a while, but a colligative property is something that changes about the liquid depending on how much stuff you have dissolved in that liquid. So when we're talking about colligative properties, I don't care what is dissolved in my water. All I care is the amount of stuff dissolved in my water. So some things that change based on colligative properties are boiling point. The boiling point increases. Freezing point decreases with more stuff you have, and osmotic pressure, the pressure of water. And that's what we're mainly going to be focusing on here is osmotic pressure and this idea of osmosis. So osmosis is the natural diffusion of water from high concentration to low concentration. And plant and bacteria, they have cell walls to help minimize this water loss. Us animal cells, we don't have that luxury. Now, the cell itself can be in 3 different states based on its surrounding. The middle state here is isotonic. Isotonic is if the amount of solutes inside your cell and outside your cell are the same, then water flow going inside and outside the cell are the same. So I know the arrows are pointed. You can't really see the arrows. Whoops. But in this middle picture, water goes in and leaves at the same rate. Hypotonic. Hypotonic is if I put my cells in a solution with lower solute concentration. What will happen is that water will flow into the cells. The cells will eventually burst. This can happen to red blood cells. This happened about, over a decade ago now. The story that I think of that I always like to tell. So back when the Nintendo Wii was popular, back in the early 2000s, early or mid 2000s, I guess, there was a contest in California where it was called Hold Your Wii for a Wii. Basically, the people had to drink a gallon of water, and whoever peed the last would win. Well, what happened to one person is that their red blood cells started to burst because of all that water they ingested, and they're not like peeing it out. Their blood became hypotonic to their blood cells. And so water rushed into the blood cells, their blood cells popped, then they died. So the moral of the story is listen to your body. The other state here on the left is hypertonic. Hypertonic is if I put my cells into like a very salty solution, what will happen is that all the water will flow out of my cells and my cells will shrink. This idea of hyper, iso, and hypotonic is very important for things like blood transfusions or transfusions of liquids into a patient. You have to make sure the solute concentration of what you're putting into someone is isotonic to their blood cells. Otherwise, you're going to make their blood cells go hypertonic and hypotonic, which will cause big problems. So just to assume that we have this, or just to check that we have this concept down, I have two final questions from this PowerPoint. I do have another poll for this. So let's say your blood cells have an internal salt concentration of 150 millimolar. Then I put them in a beaker full of water and 500 millimolar of salt. All right, so A and B. A, water can move, but not ions. What will happen? B, if you allow ions to move, what directions would they move? So let me pop up the poll. Think about that one. Tell me if I'm permeable to water but not ions, what am I going to make? And if I'm permeable to ions, what's going to happen? It'll take about a minute or so to answer this one. And as always, if you have questions, feel free to put them in the chat. You can send me a private message as well if you would like. We'll go about like 15 more seconds and we'll talk about this. All righty. So it seems like we're, as a class at least, of the people who are here, we are more comfortable with the idea of the water movement than the ion movement. So I like to draw pictures of this, right? So my cell has 150 millimolar. My beaker has 500 millimolar of salt. The general idea is these two concentrations are going to end up the same eventually. So if I don't allow ions to move, the way that these two numbers are going to be the same is by water leaving the cell. When water leaves the cell, the concentration inside goes up, the concentration of salt. Because remember, if you remember from general chemistry, concentration is moles divided by liters. So the more liters, the less liters I have, therefore the higher concentration. So water is going to leave the cell and this is hypertonic. While in B, if we have the same picture, if I'm allowing salt to move now, again, these numbers are going to try to equal each other. And so how that happens is a net movement of salt into the cells. So water will move out of the cells, and if able, salt will move into the cell. All right, any questions about that? All right, so let's move on to the PowerPoint that was for today. And in this PowerPoint, we're going to talk about buffers, acid and bases, because proteins are made out of amino acids. So it's kind of important to know how they work. And for experimentation, we always use buffers. So some basic definitions for us. An acid is something that donates a proton, pH decreases. And while I'm talking about pH, anytime you see this lowercase p in terms of a mathematical equation, it always means minus log, negative log. So pH is negative log of hydrogen concentration. That's what pH means. So an acid will donate a proton to the environment, pH goes down. Bases accept the proton, pH goes up. When an acid donates a proton, it becomes a base, which we call the conjugate base. So here HA is going to A. When a base accepts a proton, it creates conjugate acid. So here H2O is our base. It accepts a hydrogen and forms a conjugate acid. In biochemistry, we're going to shorthand H plus all the time. So here we have acid going to H plus conjugate base. Just realize a proton by itself like this doesn't exist inside of cells really. What is happening is that you really make H3O plus when you say H plus. So you always make hydronium, which is H3O plus, but for the sake of simplicity, people just write it as H plus. Here on our second equation, we have our base that's accepting a hydrogen from water, and BH is our conjugate acid. So every acid will make a conjugate base. Every base will make a conjugate acid, and those are called conjugate pairs. So just to get us comfortable with this idea again, I have a couple acids here. I want you to draw me the conjugate bases. And then the C and D, I have a couple bases. I want you to draw the conjugate acids. So we're going to take a minute or so, see if you can figure out conjugate pairs by looking at structures now. As always, if you have questions, let me know. All right, so let's take a look at this in case you're not quite sure, or if you do have answers. So I have acids. What's the conjugate base? So the base means it has an extra proton, and that's the difference between a conjugate base and an acid. Or sorry, the bases have one less proton. I said that backwards. So when you're looking at conjugate pairs, the acid always has one more hydrogen than the base. And usually when you're talking about acidic hydrogens, they come from groups that are charged or from oxygens mostly. So here we have NH3. If this is an acid, then the conjugate base would be NH2, loses a hydrogen. It's never going to lose the hydrogens from the carbon. They're not acidic enough. They're not polar enough. Same reason why they can't hydrogen bond. B, it might be tricky to know which one to take it from, NH3 or COOH. You actually take it from COOH first. Carboxylic acid is a very strong acid, so that's going to lose its proton. Here's the same idea. I'm giving you bases. I want you to make the acid. Again, the thing to keep in mind between acids and bases, an acid just simply has one extra proton if you're talking about conjugate pairs. So here I can put a proton to make my conjugate acid. D, same idea. You put it on the negative charge to make your acid version of your base. So those are some conjugate pairs for us. Any questions about acid bases, conjugate pairs up to this point? All right. Now we're going to talk about acids and bases in terms of pH. All right. So water itself is neutral, but it does what's called autoionization. Water is both an acid and base, and so it will react with itself to form H plus, or really hydronium, H3O plus, and hydroxide. All right. And the amount of H plus to OH minus is a constant at different temperatures. So every single temperature has a different amount of H to OH. At a temperature of 25 C, when you multiply the hydrogen concentration by the hydronium concentration by the hydroxide concentration, which is called Kw, or the ionization constant of water, you get this value every single time. Does not matter what you put into water. As long as water is 25 C, when you multiply the hydronium concentration by the hydroxide concentration, you will get the same exact number every single time. Different temperatures, you get different numbers, but at this temperature, you get the same number. If hydrogen and OH minus concentrations are equal, this is neutral. And at 25 C, they're both equal to 1.0 times 10 to the minus 7. If you have more hydrogen than OH, you are what we call acidic. If you have more OH than hydrogen, you are what we call basic. Now, talking about pH again, pH is just minus log H concentration. So if pH is 7, you're neutral at 25 C. One thing that I like to ask students, the test, if they have this idea down, is that I put on my test, water's at 60, Kw is some other number than 1.0 times 10 to the minus 14. Let's say 1.0 times 10 to the 15. What's pH? What's a neutral pH? About 70% of people will put 7 without thinking about it. So remember, 7 is only neutral at 25 C. Any other temperature, 7 does not mean neutral. All right, if pH is less than 7, you're acidic. If pH is greater than 7, you're under basic conditions. There's also POH, which is the opposite of pH, but we're not going to talk about POH. We only talk about pH. Any questions about those ideas? All right. So let's do some Gen Chem 1/2 calculations because biochemistry uses buffers a lot, uses acids and bases a lot. So the first one I will do for us. And then the second one, if we have time, I'll let you do that. Okay, so calculate the pH of a 200 milliliter solution of pure water to which 50 milliliter of 1 millimolar acid has been added. So first off, some terminology. Strong acid. A strong acid means you give all your protons, 100% of the molecules will give their proton away. A weak acid is less than 100%. To make things simple, we're usually going to talk about strong acids in this class. Again, I like to draw pictures. Helps me to think about word problems. I have 200 milliliters of water. And I have 50 milliliters of 1 millimolar acid. I put that into my solution. And I want to know what's pH, which is minus log of H plus concentration. Right? So to solve this, the variable I need is the H plus concentration of my combined solutions. And hopefully you remember from general chemistry, when things are in brackets like this is concentration or molarity, which is moles divided by liters, right? So that is molarity. So really, I need to find out the molarity of my concentration, or hydrogen. There's a couple ways to do this, but the easiest way is this equation, whoops, that I know general chemistry students love because it's so simple and they love it so much they use it on things that they're not supposed to use it on, but we can use it here. This is called the dilution equation, right? Molarity of solution 1 multiplied by volume of solution 1 equals molarity of solution 2 multiplied by volume of solution 2. So now I need to start declaring variables, and it doesn't matter what you call molarity 1, what you call molarity 2, as long as you're consistent. So one of my solutions is the acid solution before mixing, and the acid solution is 50 milliliters. So I'm going to say that's volume 1. And the molarity of that, well, that is 1 millimolar. So I'm going to call that M1. If I call that V2 and M2, that's fine. All right, my second solution is the one I care about, is what's the pH of this solution, of my new solution. So my second solution, the molarity of acid, or M2, I don't know, right? That's what I'm trying to figure out. I do know the volume though. V2 is 250 milliliters. You might be tempted to say it's 200, that's why I like to draw out the picture, slow myself down and see what I'm doing. I'm taking 200 milliliters of pure water and adding 50 milliliters of stuff to it. Therefore, my new solution has a volume of 250. From there, we plug in M1V1, M2V2. So M1 was 1. V1 is 50. M2, I don't know. V2 is 250 though. You don't need to convert to liters. You don't need to convert to moles. As long as each side is milliliters and each side is millimoles, it'll work out just fine. When you do this, if I did my math right, and if I can read my writing, I believe you get, was it 0.20? Is that what I have written down? Times 10 to the minus 3. Let me do this really quick because I write like a chicken. Equals 50 divided by 250. Yep. And that 0.3 is because it's molar. When you do this calculation, you'll probably get 0.2 millimolar. And I already converted it into molar for us. And the reason is because I want pH. Remember pH, whoops, I have it written over here. pH is minus log hydrogen concentration. Hydrogen concentration is moles divided by liters, or molar. Big M means moles divided by liters. So to figure out the pH, I just do minus log of the hydrogen concentration I just calculated, which is 0.2 times 10 to the minus 3. The pH of this solution is 3.7. All right. So is there any questions about my logic, about how I went through and solved that problem? Any place where you got lost, couldn't follow me, or anything like that? Any numbers that you're seeing that you're not sure how I got? Okay, well, so for the next couple of minutes, try and do B. See if you can get B. Again, I do hope you're trying, because like learning any skill, like learning how to play basketball, you can't just watch someone do it and expect to know how to do it. You actually have to get on the court and practice. To do these equations, you have to practice them. So let's see if you can tell me, how much 10 millimolar acid do I need if I want to make a solution that has a final volume of 50 milliliters and a pH of 2.1? And if you get stuck somewhere, not sure how to begin, please let me know, and I'll try to help out. We do have a question. Not sure where to begin with B. Yeah, so B is a little bit weird compared to A. So again, I like to draw pictures here. So I want a solution that's 50 milliliters pH 2.10. Now I have a solution that's 10 millimolar acid. And let's just say the volume is infinite. I have an infinite amount of 10 millimolar acid. How much do I need? Well, to really solve this, I need to know what molarity of acid or how much acid that I need to add, right? And in my final solution, I'm given a pH. So the first thing I need to solve for is, what is my hydrogen concentration in my final solution? It's given, but not in a form I can use. It's given in pH. But we can solve for that because remember, pH equals minus log H plus, which equals here 2.8. Or sorry, 2.1, not 2.8. And I can move the negative around and say log of hydrogen equals negative 2.1. All right. So something about math, if you have a variable, which we do, H plus, that is inside of a log, you can't do anything to that variable until you get rid of the log. The only way to get rid of a log is to do 10 to the power of each side. So doing 10 to the power of log eliminates both the log and the power of 10. But in math, if you do something to one side, you have to do it to both sides. So my hydrogen concentration inside my final solution equals 10 to the power of negative 2.1. When you solve that, you find out that the hydrogen concentration I want inside my solution is 0.007943 molar, or 7.943 millimolar. Either way. So to have a pH of 2.10, that means I have a concentration of 7.943 millimolar. From there, I'm set up to do M1V1 equals M2V2, right? I'm going to say my solution 1 is my 10 millimolar acid solution. And my solution 2 is my final solution, or the solution I want to make, or my end solution, I guess. So molarity 1 of my first solution is 10. How much do I need of this? I don't know. That's the question. How much of this solution do I need? So that's my variable. For my end solution, I just figured out that the concentration that I need is 7.943, and I said my final volume is 50. Now I can solve for V1. When I solve that algebra, I get V1 equals 39.71 milliliters. So to make this solution, I need to take 39.71 milliliters of my acid solution, and I'm going to add that to 10.29 milliliters of water. That will give me a 50 milliliter solution at a pH of 2.10. So those of you who want to work in a lab that does experiments, B is a calculation you'll probably be doing a lot. It's a simple calculation to figure out how to make different solutions at different pHs if you start with an acid of known concentration. All right, so with B, I know that one's a little hard to think about, but now that you see it worked out, is there any questions of what I did there? Any of the logic steps I made, how I got any of those numbers, or anything at all? All right, if not, as always, I will put up a homework that deals with the stuff we went over today. Remember, your first assignment is due Friday. I assign them every Monday, Wednesday, Friday with lecture, and you have a week from when I assign them to do them. If you do have questions about anything at any point, don't hesitate to email me. Other than that, I have nothing. Well, I have a lot more for you, but not for today. So with that, hope you have all good rest of your day. See everybody later.